Hey guys, so today I'm gonna report a topic about climatic variance. But first, let me show you the topic outline. Semi-arid environments. Semi-arid environments are a subtype of dry land with a aridity index between 0.20 and 0.50. In semi-arid regions, soils have frequently been degraded by historical land use, resulting in low soil organic carbon content and poor structure. Wadis, also called as arroyos, refer to ephemeral channels in semi-arid environments. These are desert valleys. They are normally dry but subject to flash floods from isolated rainstorms. Reinforced concrete and gabions are essential on downstream side, where scour and undercutting are most destructive. Next is selective erosion, caused by slow weathering. Leaves residual in Silberg Mountains, flat-top mesas and pillar buttes in bedded rocks, and natural arcs where weathering breaches thin rock ribs. Desertification. It is a slow loss of vegetation and expansion of desert, as in African Sahel, due to any or all of climate change, deforestation, overcropping, overgrazing, and soil salt increase by evaporation of irrigation water. Next is desert sediments. Alluvial fans. These are banks of flood, sediments, and debris flows from mountain wadis. May coalesce into bahada, forming the mountain in-foot slope with a sediment apron over a sloping bedrock pediment. Sediments are deposited rapidly, so are unsorted and poorly consolidated. Alluvial plains. These are extensive lower reaches of fans, mainly sand and gravel in shallow, braided wadi channels. They are coarse cobble beds remain from wet Pleistocene climates. Playas. These are flat floors of inland basins with one fine, soft, weak silts and clays often thixotropic. Salt and gypsum form in temporary evaporating lakes. Sabka. They are similar but with limestones in coastal zones. Salt. These may form thick beds in playas and sabkas. They are also left by evaporation in clastic sediments. Capillary rise in fine soils may lift salt 3 meters above water table into roads and built structures. Salt crystal growth is major form of desert weathering of rock and concrete. Impermeable, dense concrete suffers less from salt breakdown. Jury crusts. These are surface layers of cemented sediment, mostly sand or gravel, mineral cement deposited by evaporating groundwater. The most common jury crust is calcrete or calish, cemented by calcite, about 1 meter thick over unconsolidated sediment. This should not be confused with rockhead as bearing capacity is low. Loess. They are structureless, yellowish, calcareous, silt of grain size 0.02 to 0.06 mm common in interiors of the northern continents. Dry or moist, loess will stand in a vertical face, but it is easily gilled and piped by running water. And it disaggregates and collapses on saturation, hydrocompaction. These are the following sample images of desert sediments. Blown sand. Wind moves dry sand by sliding, rolling, or bouncing, also known as saltation. Sand abrasion undercuts rocks and structures close to ground level. Deflation removes sand, leaving desert pavements or polished pebbles. Dunes. Dunes are built by deposition in slack air, in eddies, and in the lee of obstacles. They may be longitudinal or transverse to prevailing wind, irregular in shape, or crescentic by chance. Stabilization of migrating dunes may be achieved by trapping the sand with induced vegetation cover, or with fences and shelter belts, but impractical if sand supply is too large. Corrugations, also called as washboarding. Corrugations on dirt roads develop on dry, well-sorted sands. Worst are dune sands. Damp, well-graded soils are stable. Tills and glaciofluvial sands are the best because the clay content fills pore spaces. The table below will show you the different zones like mountains, pediment, alluvial plain, and playa with their different characteristics like their slope width, process, sediments, drainage, and hazards. Also, there's a picture below that shows the different setup and formation of different types of semi-arid environments. Next is periglacial environments. Periglacial environments are areas adjacent to and beyond the limit of glaciers. A zone of intense freeze-thaw activities produces periglacial features and landforms. Cold climates with limited snowfall and with no ice cover are periglacial, locally peripheral to glaciers. Permafrost. They are permanently frozen ground to depths of 10 greater than 200 meters. If permafrost is less than 50 meters thick, it may be discontinuous. They may include lenses of pure ice within soil and rock. Active layer. Zone of summer thawing and winter freezing, generally 0.3 to 5 meters deep. They are permanently frozen ground beneath, prevents drainage, leaving it saturated, unstable in summer, causing widespread slope failure and subsidence. Structures and sediments. Landslides. Landslides and solifluction are common in active layer. Camber folding. These are valley bulging increase. Ice heave. Ice heave and collapse forms irregular cryoturbated ground, sediment-filled ice wedges, patterned ground with stone polygons, all create disturbed and vertical boundaries in soil active layer. Frost shatter. This is extensive. They are commonly to 10-meter deep in chalk of southern England. Scree, also called as talus. This is a coarse, angular slope debris with an angle of repose equal to 37 degrees, masking cliff foot profile. Many fossil Pleistocene screes are inactive in modern climate and so gain vegetation cover. Lowland. These are periglacial sediments that include outwash gravels, alluvial and blown sand and extensive loess. Clay with flints. This is a soliflucted mixture of residual soils and tertiary clastic widespread but generally thin on English chalk outcrops. This slide shows you the different images of the different types of structures and sediments. Solifluction. This is the downslope movement of saturated debris, a type of wet soil creep moving about 1 meter per year. It can occur on any saturated slope, but it is most common in the summer thawed active layer of periglacial slope which cannot drain through the deeper permafrost. Head. It is an unsorted, soliflucted debris. It may appear similar to glacial till, but it is formed entirely of local upslope material. Head can flow by plastic deformation, but it is typically well sheared with basal, intermediate, and circular slip surface. The shears reduce the strength to low residual values. Head forms most easily on slope of shale. Mudstone, clay, and chalk combined rock is chalkhead. Solifluction flows. It is up to 1,000 meters long. It may move in slopes as low as 2 degrees. It is commonly 2 to 4 centimeters thick, but may accumulate in layers to depth of greater than 15 meters on concave slope and as valley in fills. Next is permafrost engineering, where it involves subsidence, conservation, block supports, piles, utilidors, and gravel pads. Subsidence. Flow and heave occur poorly drained silts and clays when ground ice is melted. Sands and gravels are generally though stable. Conservation. The conservation of the permafrost is generally the best means of ensuring ground stability for built structures. Any disturbance of the natural insulation provided by the soil and vegetation increases summer thaw and depresses permafrost beneath buildings and roads. Block supports for heated buildings with clear airspace beneath can be stable on gravel active layer over preserved permafrost. Piles. Piles into stable frozen ground generally need to reach the depths around 10 meters. Utilidors. They are pile-supported conduits built in streets for heated services, pipelines, and cables. Lastly, gravel pads, also called as embankments. They are a few meters thick, can be enough to provide insulation and let the permafrost expand into them, stabilizing the compacted active layer. Internal cold air ducting or insulation layers of peat or wood chips further improve conservation of the permafrost and protection of the structure. And that's all for my report. Thank you for listening.